Recording is on. Yeah. Okay. So guys, so listen. So you have your symbol here in the center, right? You have your mass number up here at the top. Remember, mass number is protons plus neutrons. So far, so good? Down here at the bottom, you have your atomic number down here. And that's your number of protons. That's all I care about so far. We don't have to worry about the charge just yet. Now, you might see this on your ACT sometimes. They actually call this X, A, and Z, where A is your mass number and Z is your atomic number. Why they chose to call them these letters, I don't know. It wasn't my decision. Okay? So if I said A equals 15 and Z equals 4, write the symbol. Because that's the kind of thing they'll give you on an ACT test. So, what does Z represent? Atomic number. So you look on the periodic table, and what's the atomic number of 4? What element? Beryllium. So I'd write a Be. Okay, it's up here. It's up here, the 4, right there. Okay, those are the atomic numbers. Atomic number of cesium is 55. The atomic number of tungsten is 74. Atomic number of copper is 29. That tells you how many protons there are. The atomic number is the number of protons. So we put that down here at the bottom. We put the 4. We put the 15 up here at the top. Does that make sense? How many neutrons are here? Okay, 11. Basically, you just subtract these two, right? The number of neutrons equals 11. Does that make sense? Yay or nay? You good?
Wait, to get what? The number of neutrons?
Yeah, the number of neutrons. This is protons plus neutrons, and that's just protons. Just subtract the 2 to get the neutrons. We won't worry about charges just yet. So far, so good? Yeah? Okay, let me give you something to work on for recording and tracking. Okay, so now, some notes here. Real quick. Okay, so let's look at some notes. And guys, you need to stop talking, please. Okay, so we can move forward. Oh, let me turn this back on. Okay, so here's what you need to know. The atoms make up everything. Atoms come together to make up elements, and Mason, and everything is made up by elements. There are 3 subatomic particles. In the nucleus, we find what 2 things?
Protons and neutrons.
Good job. Protons and neutrons are in the nucleus.
Electrons are around it.
Good. Electrons are around the nucleus. Kind of looks like an egg. So electrons are out there. But protons are positive. Electrons are negative. And neutrons have no charge. You've got that so far, yes? And we know that the mass of the atom comes from the nucleus. The mass number is how many protons and neutrons you have. Okay? So if I had identical twins, standing here, and I know they both have the exact same DNA. They're identical. They have the same number of protons. Protons equal protons, right? But this guy is a little heavier. It looks like his little face is a little heavier. His neutrons do not equal the neutrons of his identical twin. They each have their own mass. Twin 1, let's say, has a mass of 22, and twin 2 has a mass of 20. Although they're the same DNA, the same number of protons, they have different masses. That's what isotopes are. They have the same mass, same number of protons, but different masses. Does that make sense? Yes or no? Okay, good. So the atom consists of a nucleus and protons and neutrons and electrons on the outside. And you should know their charges and things like that. Okay? The atomic number. Now don't feel like you have to write all this down. This is all on Schoology if you want to look at it later. This just helps keep me mentally on track while I'm telling everybody the same things. Okay? So the atomic number is specific for each element. It's like your social security number. No two people have the exact same security number. They don't. Or driver's license number. Now they're starting to use driver's license numbers as well. Okay? So the DNA or social security number or whatever is like the atomic number. It is specific for each atom. Okay? It is the same for all atoms, so that element is equal to the number of protons. Okay, I don't worry about that. Proton gives the atoms its identity, just like your social security number gives you your identity. Electrons in the atom, we're going to assume right now that every element we talk about is neutral. So on all of these, if there's 45 protons, there's going to be 45 electrons. If there's 108 protons, there's going to be 108 electrons. Okay? So we're just going to assume that these are all neutral and that the protons equal the electrons. We good? Okay. Mass number is the number of particles in the nucleus. The mass number is not this number down here. This is called the atomic mass. It's an average. This is a weighted average of all the known isotopes for that element. A mass number is each individual atom. Does that make sense? Like these guys over here. They each have their own mass, but their average mass would be what's up on the periodic table. Okay? So, when I look at this, here's our chart. Carbon has how many protons? 6. And what's my mass number then going to be? 6. Okay, if protons are 6, neutrons are 6, what's my mass number going to be? 12. Mass number is protons plus neutrons. How many electrons will I have in a neutral atom? 6. What element has 17 protons? You should be looking at your periodic tables I gave you. Okay, look at your periodic tables. Everyone should have them out in front of you. I want to see your periodic tables up in the air. Because you were not looking at them when I was asking you to look at them. Everyone put your finger on number 17 so I know you're using your periodic tables, please. Put your finger on 17. There we go. Okay, good. Excellent. Excellent. Okay, good. Thank you. When I ask you to take out your periodic tables every time, I expect you to do that, okay? Good. It is chlorine. I'm not being tracked for some reason. Oh, it lost me. Okay, so it's chlorine. What's my mass number then? 34. I add these two together, right? So it's 34. And how many electrons will I have? 17. Electrons equal protons. Somewhere write that down. What element has 38 electrons in a neutral atom? Find it on your periodic table. Find it on your periodic table. Find number 38 on your periodic table, not the one on the board. On your periodic table. Find it. They're all in numerical order, so they're kind of easy to find. Strontium. Okay, it's strontium, Sr. How many protons does strontium have? 38. How many neutrons will it have if it has a mass number of 78? 40. Does that make sense? Yes? Okay, now, talk about isotopes real quick. They have the same number of protons, different number of neutrons. We've been through this, haven't we? Yes? So, nuclear symbol. When you write your nuclear symbol, that's actually wrong. Things got moved over. So, when you write a nuclear symbol, let's go back. Let's write a nuclear symbol for a couple of these. For the first one, I put K here. What goes down here at the bottom? What number? But what number? What is the number? 19. 19. And what number will go up here? 29. That's called its nuclear symbol. That's how we write them. Okay? So for carbon, what number goes down here? 6. And what number goes up here? 12. So far, so good? Yeah? Are we okay? Okay, good. And then, we talked about isotopes already, nuclear symbols, atomic mass. Atomic mass is that number now, the red number at the bottom of your periodic table boxes. It is a weighted average. You know what weighted is, right? Like in this class, your tests are worth 50% of your grade. You probably want to do better on tests than anything. Lab is 40%. Homework's 10%. Okay? So these are weighted averages of all the isotopes of all the different elements of that, all the atoms of the element. So if you look up here, magnesium has 3 different isotopes. It has magnesium 24, 25, and 26. Here's, we talk about the number of protons, number of electrons, number of mass number, okay? Here's our percents. 79% of all the magnesium isotopes are magnesium 24. 10% is magnesium 25, and 11% is magnesium 26. So I take a weighted average, using these percentages as a weighted average of the masses, and the actual mass of magnesium is 24.31. That is the weighted average of all the different isotopes. Does that make sense? Yes or no? Talk to me. You get that? Okay. And here are some examples of different isotopes. Lithium has 2. Carbon has 3. You see it's kind of close. Fluorine only has 1. Oxygen has 3. Sulfur has 4. And copper has 2. But the one that's in the most abundance is probably closest to the actual value. We have copper 63 and copper 65. But the actual mass is 63.55. So we probably have a greater abundance of copper 63. Okay? Just like in my classes, if I did percent of boys to girls, I think my higher number would be that in this class of girls. The greater percentage of my students is girls in this class. Does that make sense? Yes? Brett? Okay. Okay. And that is the end of chapter 4. Okay? So that's the end of chapter 4. Chapter 5 deals with atoms. Okay? I need you to be taking notes, please. Okay? And with the atoms, they talk about the electrons in the atom. Chapter 4 was the different parts. Here's my atom. In my nucleus, I have protons and neutrons. Outside of the atom, I have my electrons. We devote an entire chapter to electrons because electrons are the ones that are involved in chemical reactions. Protons give the identity. Neutrons give the bulk, the mass. Electrons are responsible for reactivity. We don't do anything with the protons and neutrons. That's called nuclear chemistry. We're not going to do nuclear chemistry. We're more worried about chemical reactions. And chemical reactions deal with the electrons. Okay? Yes? So that's why we have a whole chapter devoted to electrons. Okay, that's good. So, this is what an electron looks like in its different orbits. Okay. So, again, don't write all this down. I prefer you listen, take your own notes from the discussion. And if you want to go back and write this down later, great, but I cannot wait. I'm not going to wait till everything gets written down. Okay? So, much of what we know about electrons is due to what we know about light. Okay? We can't see electrons. We don't know where they are. But what we can see is how electrons interact with matter. We can see how electrons, we can see the effect of electrons even though we can't see electrons. And the one thing we see coming off of electrons in its interaction with matter is light. When fireworks goes off, those are electrons. When you see a spark somewhere, that's an electron. Okay? So we have to understand light in order to understand electrons. And light is part of this big group of radiation called the electromagnetic spectrum. Okay? The electromagnetic spectrum houses microwaves, UV rays, and light, visible light. We can actually see a small part of the electromagnetic spectrum, a small part of it with our eyes, and that's visible light. But there's a whole plethora of things that are in the electromagnetic spectrum. And here they are. So you have radio waves, microwaves, infrared, visible light, UV, X-ray, and gamma. If you took physical science, you've probably seen this before. If not, this is new to you. The chart is over there on the wall. I will never have you memorize all of the electromagnetic spectrum. You don't have to. What you have to do is know how to read it and understand what it means. Okay? So light is part of this electromagnetic spectrum. And we need to make sure we understand light in order to understand electrons. We know light is made up of both waves and particles. It has both. Einstein figured that out a long time ago. That it has both particle-like and wave-like properties. We know that light can move things, hence its particle nature. We know it's wave-like because we can how it affects other things. So to understand electrons, we have to understand light. And to understand light, we have to understand waves. So now we're going to talk about waves in order to get ourselves to electrons. Okay? So, parts of a wave, wavelength. A wavelength is measured in meters. It's a length. So of course it's going to be measured in meters. Its symbol is the lambda. Lambda looks like a T that fell over on its side. It's a Greek symbol. And wavelength is the distance between the top of a wave to the top of the next wave. So it's from crest to crest. If you've ever sat on the beach and listened to waves crash against the beach, whether it be a lake, a river, an ocean, each time you hear that crash, it's another crest of a wave hitting. If you measured those, that would be your wavelength. And we measure them in meters. Our meter stick. We measure them with meters. Okay? But the wave of a water wave and the wave of a light wave are much different. A light wave is very, very, very small. And we measure them in nanometers. Okay? But we'll get to that. This is our visible spectrum in nanometers. Blue has about 400 nanometers, and red is 750. This is the only part of the electromagnetic spectrum we can see. And we'll come back to this. Amplitude is the height of the wave. It's measured from the origin to its crest. It's how high a wave goes. Mason, I need you to open your eyes and take some notes, please. Okay? If not, we need to go stand in the back, okay? So amplitude means how intense this wave is. If you have a dimmer switch on any lights in your house, you're controlling the amplitude. The brighter they get, the higher the amplitude. The lower they get, the lower the amplitude. My voice. If I increase my loudness, I'm increasing the amplitude. If I bring it back, I'm reducing the amplitude. That's why they're called amps. The things that, amplifiers are speakers. You can turn up the amp or turn down the amp. Louder or lower. That's amplitude. So the higher the peak, the louder it is. Does that make sense? Yes or no? Yes? Okay. Frequency. Frequency is the letter V. It's not really a V though, it's a fancy V. It kind of looks like that. It's got like a wave to one side of it. It's from the Greek letter nu. Frequency tells us how many waves go by a point per second. We express them per second. Cycles per second. Waves per second. And you all ask me when you're doing the units, well, how can you have just a letter on the bottom and nothing on top? We have it right here. It's per second. Okay? So the units for frequency can be one of three things. Hertz is the guy who came up with frequency, Heinrich Hertz, and we abbreviated Hz. So we can use Hz as a unit for frequency. My son went to Karlsruhe Institute of Technology in Germany, and that's where Hertz did all of his work, and the laboratory is still there. It's very cool. It's also where Mercedes came up with the engine, the diesel engine, and all the stuff he came up with. So Mercedes was also there. Okay, well, it was Benz. It wasn't Mercedes. I think Benz is the one who did his work there. So you can also use Hertz or S minus 1 or 1 over S. All three of these mean the exact same thing. So you can use any of those three you would like. So this is a low frequency. This is a high frequency. High frequency is more waves per second. A low frequency is less waves per second. Does that make sense? Yes? You good? Okay. Now there's this inverse relationship between waves and frequency. Do you know what inverse means? reverse. One goes down, the other goes up. Okay? The more I exercise, the less I weigh. So if I exercise a lot, my weight goes down. Does that make sense? It's that kind of teeter-totter. So waves and frequency are inversely proportional. And it looks like this. It's because of this. So if I have a wave that looks like this, it's a nice long wave. The wavelength is long and the frequency is low. It's very low frequency. But if I have a frequency that looks like this, the wavelengths are very short, but the frequency is great. So we shorten up the wavelength, but the frequency gets greater. Does that make sense? Yes or no? Okay. So there is this relationship between wavelength and frequency. When one goes up, the others goes down. Are we good? Okay. Now we're going to calculate wave speed. And as we go through this, I'm going to explain to you what I want you to do. And actually, I think I'm going to just put it up here. So if you look over here, here's your three parts. This is my equation for the speed of light. C equals lambda V. That equation is on the back of your periodic table in a little box named light equations. C is for celeritas. It means light in Latin, or aura, or glowing, or something. And C is the speed of light. Its units are meters per second. Wavelength, obviously, is measured in meters. And frequency is per second, S-1 or hertz. Now here's how I would like you to set up your problems. This is what I require for a 5-point grade. Okay? Each problem is worth 5 points. So if I have this problem, the short wavelength of the color blue are dispersed more by the molecules in the atmosphere than the red are. That's why the sky looks blue. There's light coming through. You see over here, as light comes through the atmosphere, the blue gets dispersed and the red continues straight through. And that's why we see blue skies. Okay? So, if blue light has a wavelength of 475 nanometers, so if my wavelength is 475 nanometers, what is my frequency? So I look and say, well, I need an equation. Lights are coming on. So my equation to find the frequency is C equals lambda V. You get 1 point for your givens. So I know the speed of light is always 3 times 10 to the 8th meters per second. That is a constant. It'll always be 3 times 10 to the 8th meters per second. This is also on the back of your periodic table. Then you have to write your equation. So far, so good? But look at this. My wavelength is in nanometers, and my speed of light's in meters. Can I use both at the same time? No, I can't. I need to get my nanometers to meters first. So guess what comes in? It is your metric conversions. Okay? So I need to multiply this to go from nanometers to meters. So nanometers goes at the bottom, meters goes at the top. Remember I told you everything's going to come back, every chapter is going to come back and be part of the next chapter? Okay? So meters is the larger of the two units. Nano is 10 to the 9th. So it's actually 4.75 times 10 to the negative 7th meters. That is my unit. Okay? So you must get it into meters before you do anything else. Then my equation again is C equals lambda V. I rearrange mine always first to get my unknown to one side and my other stuff to the other. So if I'm looking for frequency, frequency equals speed of light over wavelength. I just rearrange the equation. Yes? You know how to do that? Then we substitute in our numbers. So we say, okay, 3 times 10 to the 8th meters per second. On the bottom is wavelength, so it's 4.75 times 10 to the negative 7th meters. See how there's a meter at the bottom and a meter at the top? They cancel each other out, don't they? And look what we got. Per second. It's going to give us frequency. Per second. So then I divide 3 times 10 to the 8th. Divided by 4.75 second e negative 9. And I get frequency equals 6.32 times 10 to the 14th 14th s minus 1. Does that make sense? 2 digits after the decimal place. You get 5 points. 1 point for your given, 1 point for your equation, 1 point for substituting, a point for your answer, and a point for your unit. 5 points total. Does that make sense? Talk to me.
How do you get the S minus 1 again?
Because it's 1 over S. 1 over S is the same thing as S minus 1. Just like if you have 1 over A, that's A, equals A minus 1. Because it's a negative. As it goes back into its reciprocal value, it's A negative 1.
So when we always have this problem, so we always have S minus 1 after our unit.
That's a frequency unit. Just like the unit for length is meters, the unit for temperature is Celsius, the unit for frequency is S minus 1 per second. Okay? That makes sense, just for now. Okay? Do one more and then I'll let you loose on your homework. Excuse me. Okay, so then we have, it says, next one says, microwaves are used to transmit information. What is the wavelength? So now I'm looking for wavelength. If the frequency is 3.44 times 10 to the 9th hertz. Hertz is also a unit for frequency. You can use hertz or S minus 1. You can choose. So I know I need the speed of light. 3 times 10 to the 8th meters per second. So far, so good? That's 1 point. Second point is my equation. C equals lambda V. How do I know I'm using this equation? What makes me know I'm using that equation, not some other weird one? Well, yeah, look at your givens. My given is frequency, and I'm looking for wavelength. And I know this is a constant. It's always going to be 3 times 10 to the 8th. So I looked at my givens. My givens are going to tell me what equation I'm using. Okay? Yes? So I've rearranged this. Wavelength equals C divided by frequency. I substitute 3 times 10 to the 8th meters per second over 3.44 times 10 to the 9th seconds, because it's 1 over S, 1 over S. But look how nicely this works out. My seconds cancel out, leaving me with just meters, which is the unit for wavelength, right? Are we okay? Now I do my math. I take 3 times 10 to the 8th divided by 3.44 times 10 to the 9th. And I get 0.087. Meters. 2 digits after the decimal. The 0 is not a digit. It's a placeholder. So don't give me 0.09. The 0 does not count there. It's a placeholder. Okay? Are we good? Okay. So, what we'll do